Okay, welcome to the machine learning class. And in this video, we are going to learn about the classification using KNN networks. So in this video, we are going to try to learn the KNN for solving the classification problem. And what is KNN networks? KNN networks is a simple classification model that uses similarity with nearest neighbors, and KNN predicts the class of an unknown observation by the class of the largest proportion of the k-nearest observations. And KNN uses distance to measure similarity between observations. So actually, the KNN is one of the simple classification algorithm to classify the uh, the data based on the k nearest neighbors, based on the number of the nearest neighbors. Okay, as you can see here, we have the data. Let's say that we have a triangle data, green triangle data, and also red star data. And these are the training data set that we have. Then on the testing data set, let's say we have a new example or new data observation in testing data set, then we will classify this new data set based on its nearest neighbors. And in this example, if we only consider a 1k, yeah, so we set the number of k equal 1, then there is one observation from class A closest to the new example. Let's say this data, yeah, is the nearest neighbors from our new example data here. Then if we only consider 1k, yeah, one nearest neighbor, so we can say that this new example or this new data is on the class A. Yeah, class A, it means the stars, yeah, the red stars. And the new example is classified as class A because we only considers k equal 1 or 1 nearest neighbors. So what if we considers more than 1k? In this example, we consider k equal 5. Then we can say that there are 5 nearest neighbors from our new example data. And we can say that only 2, yeah, only 2 nearest neighbors, yeah, that close to the new example data. But we have a 3, yeah, we have a 3 nearest neighbors for class B that nearest to our new example data. Then we can just vote, yeah, that this new data will be a class B because there are more nearest neighbors to class B than the class A. Yeah, there are 2 observations from class A and 3 observations from class B closest to the new example. And the new example is classified as class B. And for choosing a value for k, yeah, we can calculate the distance of unknown observation to all training data, and we can select a k observation in training data that are nearest to the unknown observation, and we can say it's as a k-nearest neighbors. And we can predict the class for the unknown observation by the class of the most proportion in k nearest neighbors. It means uh, let's go back to our previous slide here. We are doing a vote, yeah, for a new example data, yeah, because there are more class B that nears to our new example data. So this new example data will be classified as B. So we can say that predict the class for the unknown observation by the class of the most proportion in k nearest neighbors. And for calculating the distance, yeah, some distances can be used to measure the similarity between two vectors x and y. Okay, so it means we have 2 vectors x and y. X and y is, we can say that, let's say that x is the training data or the observation that we have before, and the y is our new data. Then we want to measure the distance between the x and y. Yeah, let's say the x and y is two two observation data. Okay, x as, yeah, the observation that we have before, and y is our new observation. And there are three distance measures, which are Euclidean distance, Manhattan distance, and Minkowski distance. And the first one is the Euclidean distance, and these are the formula for calculating the Euclidean distance. So because x and y are vectors, then to calculate the Euclidean distance, we can use this formula. So dx comma y, this is the Euclidean distance, equal square root from the sum of xi minus yi square. For example, we have x and y like this, and x has two features and y also has two features. Yeah. So we need to make sure that x and y has the same dimension. Okay. So 1 minus 4 square plus 2 minus 6 square. Then we square rooting this calculation. Then we have a 5. So the distance between x and y will be 5. Yeah, it's like when we are calculating the what is it called? We calculate the Pythagoras formula. Yeah, it's similar with how to calculate the Pythagoras formula. And for the Manhattan distance, we have dx comma y equal absolute of xi minus yi. Then we summarize all of the observation. So for example, it's 1 minus 4 and 2 minus 6. Then we have 3 plus 4 equals 7. And the last one is Minkowski distance. We can use this formula for calculating the Minkowski distance. Yeah, the sum of the xi minus yi, absolute xi minus yi to the power of p. Then we squaring by 1 divided by p. Yeah, for example, it's 1 minus 4, and 2 minus 6. Yeah, we set the p equal 3, then we have 91 to the power of 1 divided by 3, then we have 4.5. So Minkowski distance, Manhattan distance, and Euclidean distance are the distance measures. So we can choose one of them for calculating the distance between the Euclidean between two vectors, right? And how to determine the best k in KNN? So the value of k is related to the error rate of the model, and there are no exact methods to determine the best k. And a small value of k can lead to overfitting, but a big value of k can lead to underfitting. So what is the overfitting? Overfitting is the model has good performance on the training data, but poor performance on the testing data. And the underfitting, the model is not good on the training and testing data. So it means underfitting is the worst case, yeah, in our model, because we cannot has good performance not only on the training data set but also in testing data set. And the heuristic method can be used to determine the best k, and we can derive a plot between accuracy and k in a defined range, then choose the k value that has a maximum accuracy. So to determine the best k in KNN, we need to experiment with the number of k, with more than number of k. So for example, we try by using 1k, 2k until nk, then we can see that the best k that has best accuracy, then we can choose it. And for the classification accuracy, this is the measurement for calculating accuracy. Classification accuracy is the rate of the correct classification. Accuracy equal the number of correctly classified observations divided by total number of observations times 100%. And the error rate equals 1 minus the accuracy. So we will use the iris dataset, yeah, for the experiment, yeah, in classification problem. So the iris dataset has the number of instance equal 150, yeah. So it means 50 in each three classes. We have 150 observation, and we have three types of classes, and each class has 50 observations or instances. And the number of features for the iris dataset equal 4, yeah, for numeric. All of the features in iris dataset are numeric, which are sepal length in centimeters, sepal width in also in centimeters, petal length and petal width in centimeters. And for the classes, we have Setosa, versicolor, and also Virginica. So these are the three classes in iris dataset. So what is the iris dataset? Iris dataset is a flower. So the iris is a flower which is has three types of classes: Setosa, versicolor, and Virginica. So we can see that these are the picture of the iris flowers. We have petal and sepal. Petal it means the flower, yeah, the flower in this position, yeah, and the petal is the flower on this position. So we have two types of flower here. Inside the iris, we have this one and also this one. So sepal is in this position, petal is in this position. And petal and sepal has width and length, and we use that features to classify the iris dataset. So we have petal and sepal, petal and sepal, petal and sepal. Then we can see on this table, this is the sepal length, sepal width, petal length, and petal width for each flower that we have. Yeah. So for example, this one, sepal length equal 5.1, sepal width 3.5, petal length 1.4, and petal width is 0.2. So the class label will be setosa and so on and so on. So this is the class correlation between the feature and the output. So what does it means, the class correlation? So the class correlation uh, means that for example, sepal length has class correlation 0.7826. So it means it has a proportional, what is it called? It has the uh, so it means that if the sepal length and the class correlation equal 0.7826, so this is the positive number, the class correlation in positive numbers. So it means sepal length has a directly proportional with the class. So we have three classes here, right? We have three classes, Setosa, versicolor, and Virginica. So each class will be represented as a number. For example, Setosa equal 0, versicolor 1, and Virginica 2. So we label each class with the number. Then what does it mean if we have sepal length 4.2, 70.9, and 5.84, and the standard deviation 0.83, and class correlation 0.7826. So it means sepal length and the class correlation, the correlation between the features of sepal length with the class is directly proportional. The higher sepal length will make the higher levels of the class. Okay, so as you can see here, not all of the feature has the positive correlation. Like this feature sepal width, it has negative correlation with the classes. So it means the higher sepal width will make the class uh, lower. So it means the higher sepal width will make the class lower. The level will be lower. Okay, so it is the directly proportional or inversely proportional. So we can say that the petal length and petal width are the features that has high correlation with the class. So it means petal length and petal width is directly proportional with the class. So we can say, and we can discuss it later. Petal length and petal width is the features, the features that need to be considered to classify the class, to classify the colors. Yeah, we will be discuss it later. If we only use these two features or one of these features, only these two features or one of these features to classify the iris dataset, it will have a higher accuracy. Okay, so the class correlations is useful for feature selection. Yeah, we can say that the feature that has high class correlation. Yeah, so we need to choose that features to classify the iris dataset. As you can see here, this is the correlation, yeah, between each features to the class. So as I was mentioning before, zero, yeah, let's say that zero is uh, the class Setosa, and one is versicolor, and two is Virginica. So we can say that the Sepaleng, yeah, Sepaleng, and yeah, Sepaleng has a class correlation 0.7826, yeah. Then it means, yeah, it is directly proportional with the class, yeah, because the higher of the Sepaleng will make the class also higher. But if we compare with the petal length and petal width, actually petal length and petal width has more higher class correlation with the class, right? Because like this one, we can say that this sepal length has some of the yeah, observation, yeah, that uh, let's say that this is the class, yeah, this is the class one with the SEPA length 5 to, let's say, to 5 point something, yeah, this is the observation is in class 1, right? So it means the high correlation, yeah, high correlation can be depicted with petal length and petal width, right? And what about the sepal width? Sepal width has the negative correlation with the class. So as you can see here, this is the sepal width, yeah. So we can say that the petal length and petal width is better for classifying the iris dataset. So how to train the KNN for iris using all features with scikit-learn networks and k-networks classifier. So this is the code for classifying the iris dataset by using the k-NN networks. So yeah, let's try on the Google Colab. So we will use the iris dataset. Then we can load the dataset from the scikit-learn library. So we need to import the scikit-learn dot datasets, import load iris. Then we define the variable for getting the iris dataset, iris equal load iris. Then we define the observations, yeah, for the features x equal iris dot data. So it will get the iris features. Then the y will get the iris labels, right? Okay, let's execute the code first. Okay, so we get the x and y for our data set. Let's see the shape of x variables, x dot shape. Okay, we have 150. Yeah, we have 150 data set, and each data set, each observation has 4 features, right? Like I was mentioning before, we have 3 classes. Each classes contains 50 data sets, right? Okay. Then the next one, we need to train and split the data set, yeah. So let me add this to, yeah, let me add the text cell here. So this one is, uh, let's say this is classification using KNN. Then the first step will be load the dataset. Okay, then we split the dataset. Split the dataset into train and test set. Okay, yeah, we can use the library from scikit-learn, scikit-learn.model selection, import train test split. Okay, then we define the x train, x test, y train, and also y test equal train test split. Then the first parameter will be the x and y. The first and second parameter will be x and y. And then the third parameter is the number of test size. Yeah, we define the test size to 40%. So 40% for training, for testing, sorry, and 60% for training. Then we set the random state equal 1. Okay, okay. Then the next step is we want to know the minimum and maximum value, yeah, for our data sets. So it means we want to know the statistical measure, yeah, statistical measure for each features, yeah. Then let's say we want to know the minimum and maximum value for each features. So this one is minimum. We want to know the minimum value of the uh, x, yeah, x dot min, and the x is equal 1. So it means we want to know each minimum values for each features, yeah. So this one, let's say this is the, sorry, it is not x is equal 1, but x is equal 0, because we want to know for each column, yeah. So we can just copy this one, minimum, maximum, maximum, min, and standard deviation, STD. Okay, so this one will be max, and this is will be min, and the last one is STD. Yeah, we want to know the minimum values for sepal length, sepal width, petal length, and petal width. So this is the minimum value for the sepal length, sepal width, petal length, and petal width, right? So the first column represent the sepal length, the second column is sepal width, this one is petal length and petal width. And for the minimum values, we get the statistical measure, yeah, the minimum, maximum, mean, and standard deviation for each uh, features, right? So we can also get the statistical correlation between the features and also the classes, right? So we can just import the numpy, import numpy. Then we print the correlation between sepal and sepal length, ya, sepal length and class. Okay, then we just calculate the correlation by using the numpy library, numpy.core coefficient, correlation coefficient, np.core coefficient. Okay, then because the sepal length is on the wait, because correlation coefficient for the sepal length is on the first column, yeah, on the first column. So we set it to zeros, right? All of the rows, yeah, then we only get the first column like this. And we set for the y here, comma y, okay, then 0, 1. Okay, let me explain to you after this. Okay, I forgot to give the alias for the numpy. Import numpy as np, then so why we should add 0, 1 here. So let me remove this one, then print the correlation between sepaleng and class. It will give us the matrix, right? 2 times 2 matrix, right? But actually, this is the correlation between the sepaleng and sepaleng, class and class. As you can see here, it will give us a 2 times 2 matrix. But actually, we only want to get these values, right? 0, 0,78 and something. So let's say that we want to get these values, right? So let me just give the index with a 0, 1. 0, 1, it means we will get these values, right? So for example, like this. So yeah, the correlation between sepaleng and class is 0 point something, 78 something. And we can also do this for all of the features. Wait. Correlation between sepaleng, this one is sepal width, then petal length, and petal width. Okay. Okay, so we can just change this one to 1, 2, and 3. So it will give us the correlation between each features and each class. So it's similar with the values in our previous slide, right? So this is the correlation between the features with the class. Okay. So the next one, yeah, we can start to do the classification process. So we need to give another text here. Then step 4, yeah, classify using KNN. Okay. Then the first step that we need to do, we need to uh, call the scikit-learn library for the classifier, which is the KNN. First, yeah, from scikit-learn.first, import KNN first classifier. Let me check my typing. Okay. KNN first classifier. Then for calculating the accuracy, we also need the scikit-learn dot matrix. Import accuracy score. Okay. For calculating the accuracy for our classifier. Okay. So the next one, we need to import the matplotlib because we want to visualize, yeah, the correlation between the number of k and its performance or accuracy. So we call the matplotlib.pyplot as plt. Okay, matplotlib.pyplot as plt. I think that's all for our library that we need to import. Then we define the list of accuracy. So this is the variable for getting all of the accuracy for each k numbers. So we will experiment use some of the k values, not only one k values, but some of the k values. So we need to get all of the performance for each k, then we put it on this variable. So this is will be the empty list, yeah, list of accuracy. Then the range k equal range 0,31. So it means we will use the number of k start from 1 to 30 to 30, yeah, to 30, because this is excluded. Okay. Then we can do the looping process for k in range k. Then we call the KNN equal k make first classifier, with parameters the number of k, number of neighbors, yeah, equal k, okay, equals k. Then we call the fit function because this is the method for training process. KNN.fit, we put the X train and also Y train, right? Then the next one, after we do the training process, then we can predict for the X test. Y pred equal KNN dot predict with X test. X test, right? Oh, sorry, this one. X test. Then we calculate the accuracy. Accuracy equal 100 times accuracy score. Okay. So we compare the Y test and Y pred. Okay. Because this is the real Y values and this one is the Y from our prediction model by using the KNN. And we get the list of accuracy. We call the list of accuracy dot append ACC, right? So these are the experiment for using the K number starts from 1 to 30. Then we calculate each accuracy for each number of K. Then we append the accuracy values to our list of accuracy variable. Then we can just draw after this the correlation between the K number with each accuracy by using the matplotlib. And next one, we go out from our for looping process. Then we can plot the correlation between the number of K with each accuracy. So plot range K, it will be the x-axis and list of accuracy, right? Then the last one is minus star. So it will represent the symbol for the plot, yeah. So okay, we give the plt.xtics range K. So the xtics will be the range K, yeah. The xtics, yeah. Then the label, we give also the label x label to K because the x-axis represent the K number, and for the Y label represent the accuracy in percent. Okay, then blt.show. Let's execute this code. Wait. Okay, as you can see here, we have the result for each number of K to its accuracy. So I think the two number of K, 2, yeah, 2, 3, and 5, 6, 7, 8, and something get the accuracy up to 98.5%. Yeah, it's not 98.5%, but 98 something percent. So we can say that, yeah, we can just use the number of K equals to because it get the better result. It get a good result, but the more number of K will make our computation cost higher, right? So let's say that this is the best number of K is equal to. So the next one, we can also use only, this one is, we use all of the features. Yeah, we consider all of the features from our dataset to classify the IDs. But actually, we can also use some features, 1, 2, 3 features from our features in our dataset, right? So actually, the next experiment, yeah, the next experiment, we only use the petal length and petal width, yeah. So this is, yeah, let's say that this one, I give another text cell here, use all of the features. 4.1, use all features, right? Then for 4.2, use only petal length and petal width because these two features has a high cross correlation with the output, right? Petal length and petal width only. So we can just import this code, yeah, this one, because the petal length and petal width is on is on third and fourth column. So we can say that this one will be two column like this, right? Because we only want to get the column on index 2 and 3, right? 2 to the rest of it, right? It also happened to our testing set, right? Okay, then okay, let's execute this code. Okay, so yeah, we can also get same accuracy, I think, right? Okay. Uh, okay, so I think it's also get the same accuracy, yeah. But if we use less features, so it means we can reduce the computational cost, right? What about if we use other features? So it means we only use the petal length only, okay? So for the 4.2, we only use the petal length only, yeah. Use petal length only petal length. Okay, because we use the petal length only, so we can just say that this one will be like this, yeah, because we only use the column on index 2 only. Okay, okay, so let me check my code. Okay, I think the result is different with our slide, yeah, but it's okay. I don't know, maybe there are some mistakes in the slide, but actually this is the latest version for my code, so you can just use this code, yeah. And we can say that, yeah, it's also get around 98 point something percent. Yeah, if you use only petaling, so you can reduce more computational cost, right? So if we get the same accuracy with less features, so it is better, right? And the last one, we use only the petal width, yeah, for predicting the iris data set. So the last one only use only petal width, yeah, for predicting the iris data set. Okay, so this will be 3 to 4, right? Because we use the last columns in our data set. Okay, then let's see the accuracy. Okay, I think this give us a better performance, yeah. So yeah, let's say that we can back to our slide here. Okay, so because the petal length, yeah, the petal length, petal width has the highest class correlation. So it means it will make the accuracy better, yeah. It will make the prediction better than our previous experiment. But let's see uh, the exact accuracy if we only use the petal width. Okay, so let's see. We want to know the accuracy in index 2, yeah, 2. Okay, so uh, if you want to know the accuracy in k equals 2, so it means we can just print the accuracy, yeah, here. Print accuracy in of k equal to, you can just call the list of accuracy in index 2, index 1, yeah. Oh, sorry, k in range of k, so it will be 2, yeah. 1, 1, 1, 0, 1, okay, 1. Okay, k equal to 93.33%. Yeah, so it means I think it's similar. It's also similar, yeah. It doesn't make any difference if you use only petal width, yeah, and petal length. But the most important that we need to know if we can use the less features, so it will make the computational cost reduce, right? So yeah, this is the result from our classification problem. Okay, that's all for our explanation, our discussion in this video. So if you have any question, you can ask me on the Google chat, yeah. So we can just discuss on the chat. Okay, thank you.